Before I get started, quick question from my side. Are you familiar with Transmission EBSD?
A little bit.
You've read about it, you've tried it? Okay, because that's what I'm going to talk about in the first half of the presentation. So that's what I mean here by the orientation measurements in TEM foils. Now, first a little bit of background why we want to do it. So there's the high resolution EBSD. At some point you hit the limit, and then in the literature you may find, yes, Transmission EBSD is fantastic, really gets us to a new level of resolution. Let's see what it really is. So how high does it go, and what are the limitations over there? Then I'll talk about the Transmission EBSD a little bit more, some examples on how to do it. So the high resolution EBSD, when we're talking about EBSD, one of the questions I always get is, what is the smallest step? What's the smallest feature you can analyze? And I'm always going to give the most horrible answer that you can imagine. It depends. Because it depends on many different parameters. And the most important thing is the material density and the composition. So, dare I say, the typical resolution, 20 to 100 nanometer. 20 nanometer, when you have high density materials, heavy elements, then you can go really small. If you're starting to look at silicates, nitrides, really light materials, that really increases the interaction volume and thereby decreases the obtainable spatial resolution. In some cases you can optimize that by a shorter working distance, although that's mainly the imaging and the SEM. It doesn't affect the analytical resolution too much. You can lower the KV to limit the interaction volume, but also there you're limited in what you can still do. And if you're lucky, you can just use heavier materials. But typically none of us have that freedom to just go, I'm only going to work on platinum from now on. Typically you just have to use whatever you're working with. So there's the normal EBSD. Sample is at a high tilt, typically about 70 degrees. Electron beam goes in, something happens. If all goes well, a diffraction pattern comes out and we get an orientation measurement. And you can go to pretty small steps and really have fantastic results. This is an EBSD map, a normal EBSD map at 100 nanometer steps. So it's a partially recrystallized steel, you get lots of detail. And when you want to zoom into that, 30 nanometer steps, you can see a lot of substructure in there, low angle boundaries, all these wiggles that you can see in the image. But much smaller than that is not possible. You can really, sometimes you can tweak it to 15 nanometer, but then in bulk EBSD, it really stops. In some materials, as I said, you can go a little bit smaller, 10 nanometer, 25 nanometer in aluminium. I also had one with copper, but it's about the same. That's the limit for bulk normal EBSD. Then in the Transmission EBSD. So you may have read about it, you may have tried it already a little bit. What do you need if you want to do it? If you have a system, what do you need to do Transmission EBSD? You just need a working EBSD system. That's the first thing. You don't need anything special. There's no special software really. There's no special detector required. If you have an operational EBSD system, you can do Transmission EBSD. The only differences really are in your sample. It has to be electron transparent, and in how you mount the sample. So you have to have the geometry right to do it. So the sample holder has to be different, but not the rest of your EBSD system. And then you mount the sample like this. So we just had it sitting at 70 degrees. Now we go to between horizontal and -40, and the electrons shoot through the sample, get diffracted on the bottom interface of it, and then go towards the normal EBSD detector. The sample itself, this can be tricky. It's a specimen preparation. So it's let's say a normal TEM's preparation. But the thing to keep in mind is most TEMs operate at 80 to 300 kilovolts. That means the penetration power of these high energy beams is pretty high. In the SEM we cannot go higher than 30. That means that it needs to be a little bit thinner than you would normally use for TEM, or you can just see the area really close to the hole. to the edge of the sample. You need a dedicated sample holder, as I just mentioned, and you need patience. And this is an important one, because the lower the KV, the bigger the interaction of the beam with your sample, so you are going to see some thermal effects. So the moment you hit your sample with the beam, it's going to warm up a little bit, more than in a TEM, and then it starts drifting. So you have to give yourself time to let the sample stabilize before you make any detailed EBSD maps. Of course, there are many different ways to prepare TEM samples. The example I have here is a FIB lift out. So you just take the normal routines, put a little bit of platinum, a protective platinum layer on top. You mill the lamellae, you mount it on the stub or on the holder. This is a copper, so one of these half moon grids where you just solder it on with platinum, and then you thin it further until you have it electron transparent. How thin? As thin as you can get it, but typically this will be between 50 to 200 nanometer. So not ridiculously thin, and I'll show you later on why that is important, but we'll get there. But close to the edge, that's definitely where you're going to get EBSD information. Now here I have got two examples of holders. This is actually a prototype holder. We can supply the newer version of this, but I didn't have a picture of it, where you mount your sample in a little clip that you slide in on the side. It has different pre-tilt angles and different ways to mount it, so you can mount it in virtually any microscope to allow you to go to the transmission conditions. Then there's this one. This is a new holder. It's a very small one. It is this holder here. So you can, if you like, you can just pass it on, so you can just take a quick look what that is. It's also a little holder, a little clip. You mount your sample on the top, and there's a little inset. And there's a little groove where you mount your foil, and then there's this copper thing with two fingers to hold it in place. It's designed that you can slide your sample up and down a little bit depending on what you want to see. So you can also do normal EBSD if you turn it around. You don't have to do transmission. But it's nice and stable. And it's so small, you can fit it anywhere. You can use any working distance you like, and it's out of the way of any other detectors and of the EBSD detector. Now, the next question I've seen come up very often is, what is the optimum tilt? So where do I put the sample? And again, the answer is that depends. It really depends on the density and the efficiency of diffraction sideways. And so it's the composition, it's the working distance. And basically, if you increase the tilt, the whole intensity shifts up a little bit. So with the tilt, you can play with where it projects your diffraction pattern.
In that sense, this is a little bit different than the conventional. In the conventional, it's like a fixed angle.
Correct.
Almost.
Yeah. But you can conventionally, you can work between 65 and let's say almost 80 degrees. But you need to calibrate the aspect ratio for that. Here you can just play around. As long as you tell the software what your angle is, you will get good data. Now, in the literature, you may also find that you want it flat to optimize the resolution, because then your beam profile is circular. Now, if you plot it, you can see here that there's almost no deviation from circle up to about 40 degrees. And only after that, it really shoots up to a factor of 1 to 3 ellipse that we have in the normal EBSD.
So do we compromise with the resolution or the quality of the pattern with the angle?
If you go horizontal,
yeah,
and you have your EBSD here, then you have very, very little signal at the top of your screen. If you tilt a little bit, actually with, let's say, a normal EBSD position, and you tilt 20 degrees, then the electron path in the sample is the shortest. If you tilt less, then you have a little wedge of material that the electrons have to go through in the sample again. So it's not the insert, the entry point, it's the exit point that then defines what the spatial resolution is. So if you go anywhere between typically 20 to 40 degrees, you can get really good data. Now, these were the first pattern I collected on this particular sample. It's not the best patterns you've ever seen, perhaps, but they are indexable. And this is coming from the platinum protective layer on top of the lamellae. So normally we don't even look at it because that's just to protect my structure. But these grains were 3 to 5 nanometers and already produced indexable patterns. So that means that the resolution is there. And this is just to illustrate the effect of tilting the sample 10 degrees to 40 degrees. At 10-degree tilt, you have very strong contrast at the bottom and very little information at the top. And that's just because the sample is like this, and there's almost nothing going here. It wants to go down. If you tilt more, it's more efficient going up as well, and you get almost normal EBSD patterns, although in transmission mode they tend to be sharper than in bulk. So the edges are a bit sharper, so that's even nicer. Now then some examples. First a bonus when you do transmission EBSD. If you have a forward scatter detector on your EBSD system, you can do transmission forward scatter diffraction. Then the name is a bit weird, but it's an FSD diode, so let's just call it t-FSD. And your normal FSD diode is here at the bottom of the screen. And basically what you're capturing there is a fraction of the electrons that are just bouncing off the surface. So a bit of that will have diffracted information, but also some of it will just be the cone of backscattered electrons that are just basically traveling forward. When you do it in this mode, it's different. Your electrons go straight down. It's like in a TEM, you have your transmitted beam straight down, and only electrons that are scattered, are diffracted away, go sideways. And those electrons are the ones that actually hit the diode here. So this image you might consider like a dark field stem picture. So you really get information only from diffracted electrons. And because the sample is so thin, it also gives you this at really nice resolution. So you can see the detail in this image, that's 2 micron. And it's basically a solid state backscatter detector that we use for this. Now then we can just make a mapping. This is almost the entire sample that I showed earlier, where you can see a thicker part in the middle. There's the hole on one side, and on this side the hole is just outside of the field of view. 15 nanometer steps, and we can get reasonable indexing results over the entire area. Now, as first to go on this transmission FSD again, as I mentioned, the resolution you can get from this solid state diode is fantastic. 600 nanometer scale bar, and when I tried this first, I saw this grain in the middle. I just blow it up here, you see those very thin lamellae, and I said, okay, this is going to be my sample to prove that transmission EBSD has fantastic resolution, go for it. So just try to visualize that grain. That's the map. And that's the area where that grain was. It's totally invisible. That was slightly disappointing. But if you look carefully, you see in the FSD image that there's this bright band going through that grain. It's continuing. It's in the thicker part of the sample, and those 2 grains are on top of each other. So the grain with the thin lamellae is close to the pole piece, and the other side is further down. So we just don't see it. And this is the map, so also here we see that we lose some points because of the thickness. But then you go to the edge, you can go to much smaller step size. There's 2.5 nanometer steps. The scale bar is 100 nanometer. And that was the step size in the first example I showed for normal EBSD. And here you can get really fine grains. You get those lamellae that are on the order of 5 to 10 nanometer wide. So that's definitely doable. In bulk EBSD or standard EBSD, your pattern information volume is close to the surface. So that's very close to the point of impact. And whatever happens underneath doesn't really affect the pattern. It only affects the interaction, the background intensity, but not the diffraction itself. If I go to transmission, it's the beam spread that is going to affect my spatial resolution. So I put my sample like this. There's a thin foil, and the information volume is about there at the lower interface of the sample. And if I go thicker, I have more beam spread, so this red circle gets much bigger. And that's exactly what we saw happening in the previous image. Sample was thicker, the grain boundaries got fatter, so you lose the detail, and that's why. Now, when you want to optimize the spatial resolution in transmission EBSD, you can tweak that by playing with the accelerating voltage of your microscope. So the higher the voltage, the less interaction with the sample and the narrower your beam is at the point of exit. And that's illustrated in those two pictures. They're collected by a colleague from Japan. And this is at 15 kV. So normally at transmission EBSD, people are going for 30 kV electrons to have the biggest penetration power. But let's start with 15. This is the thicker part of the sample. There's the hole, that's the thinnest part. And over here you can see it doesn't look very good. So the boundaries are very broad, it's very fuzzy, and I lose a lot of detail in that image. But on the left-hand side, all the grains are very sharp, they're very well defined, and okay, that's where I get my highest resolution. Then let's try a higher accelerating voltage, 25 kV, the same area. Now you can see the grains that I could not resolve are happily resolved here. So I can get that. And that's because my interaction of the beam with the sample is less, my beam spreading is less, so I have a coherent beam at the exit point inside the grain, and I can get a good pattern. And exactly that causes a problem on that side. Because I have less interaction of the beam with my sample, fewer electrons scattered sideways, I don't have intensity anymore. So it's a balancing act, what you want to do. So the thicker the sample, the higher the high tension you have to use. If it's really thin, you have to drop the high tension to actually get a signal. Now, in the TEM software, I say you don't need special software to do it. We made it a little bit easier for you by adding a few operational modes in the software. There's a transmission EBSD configurator. And basically what that does is correct your coordinate system. Sounds complicated, it's not. If your sample is 70-degree tilted, this is the coordinate system that we use for normal EBSD to calculate the orientation that we measure from the pattern. If I mount my sample this way, I just rotate it, the coordinate system rotates along with it if I don't correct for it. And then it's going away from my EBSD detector. So basically my orientation measurement is totally wrong. What I then can do, I can there put in the tilt angle, and that basically swaps the orientation system, coordinate system to this, and I get the proper orientation that matches the exit plane at the bottom of my sample. Without this correction, I'm looking at the entry plane on the top of the sample, and that does not correspond to my patterns. Software does that based on the angle you put in over there. Another mode that we have is a very specialized mode for atom probe tomography specimen preparation. We call that atom probe assist. It's a modification of the transmission EBSD. You can select it in the TEM software. It's a special mode over there. And basically what that does, it helps you to find specific areas in your APT needle to get it very close to the apex so you can measure it with the atom probe. I don't know if any of you is familiar with the atom probe. Basically what it means is you need to get, for example, a boundary or a specific area of interest within the top few hundred nanometer of your tip. Otherwise you cannot measure it. And this is far too far out. But in transmission mode you can actually see where the boundary is, mill a little bit more until it gets closer to within the region where you need it to be. And there's a few more examples. These are coming, by the way, from our customers in Leoben at the Montana University in Austria. And also here you can see the effect of the high tension. The higher the high tension, we can actually see through those tips much better. And the tilt angle doesn't affect it too much, between 35 and 50. But if you look here in the fib geometry, if you keep your tip at 38 degrees pointed at the fib, The transmission EBSD angle is 38, which means you can mill, you can image without moving the sample at all. And in that case, the mode will just assist you in finding the proper spot. Now, just to summarize that in the end, the spatial resolution, what are the improvements you may expect from transmission mode as compared to the standard? That is for standard 7.5 kV, 20 kV, 10 to 15 nanometer, and that's on the optimistic side, depends on the material. And with transmission EBSD, you can get a factor of 3 improvement in your spatial resolution. Not much more than that, because then really the thickness of your sample starts to play in it, and then that becomes problematic. It's really, again, the diameter of the exit of your beam. Now there's a last pretty picture that I have here, a TEM foil. This is not with a fib. This is made by milling, and there's your normal SEM image. And I just want to introduce the PRIAS imaging. That's another imaging mode we have in the software that uses the EBSD detector as an imaging tool, where you can subdivide the phosphor screen in 25 blocks, and you can use each block as an imaging detector. And when we do that, we get pictures from each of those blocks that basically show a different diffraction direction. So you can see in some of the images the contrast is good over here, another one it's good over there. So you can't get it all right at the same time. But once you have that, you can just look at them all at the same time. You can average it out, and instead of having just the SE image, you can then use a picture like this, where you really see all the grains very, very nicely, and you can use this as a starting point before you go to the TEM. So you can make your EBSD map, you can look at phase maps, there's image quality, and this can be just a guide when you move to the microscope in the TEM to find the grains of interest. You know the orientations of those grains, so even special diffraction conditions, it will help you to really minimize the time needed to tweak your diffraction conditions and the specimen tilt in the TEM. So just to summarize that, the transmission EBSD, you can do it with a standard EBSD detector by changing the specimen tilt angle, working distance. There are some application-specific tools available in the software. We found that the optimum tilt are 20 to 40 degrees for the optimum illumination of the phosphor screen. Even if you have multiple grains on top of each other, it's really the bottom grain that shows the diffraction pattern. So it's not too much of a problem if the grains are so small that you have multiple on top of each other. Spatial resolution depends, as I've said already a few times. About 5 nanometer is definitely doable. The pattern formation depends on the high tension, specimen thickness, and eventually the beam spread. And then finally you can use some of the other imaging tools and normal EBSD as well to prepare your sample before going to the TEM.